Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the breadth-first search algorithm. This is a very famous graph traversal algorithm. It's the sibling of depth-first search, if you may. It's a bit more difficult than depth-first search, in my opinion, and I think a lot of people would agree with me on that, mainly because it's not as easy to implement in code. You can't just write it in a couple of lines of code like you can depth-first search. But that being said, it's not too difficult, and it is a must-know when it comes to programming interviews. So without further ado, let's dive into it. You are traversing a graph, right? And in our example, a graph is going to be a sort of tree-like data structure that's going to consist of nodes, where each node has a name, which is going to be a letter in the alphabet. In this case, A, B, F, E. And each node is also optionally going to have some children nodes. So our root node A here has B, C, and D as children nodes. B has E and F, whereas C doesn't have any children nodes. And so for our question, we are asked to traverse our data structure, right, our graph, in a breadth-first search way. And as we traverse it, we want to grab all the names of the nodes, put them in an array, and return that array at the end. So in the top right corner here, you can see this array that I've written. That's going to be our solution. Our solution, it turns out, is just the nodes in alphabetical order. And so the way breadth-first search works, basically, is that we want to traverse the graph level by level. And what I mean by that is we start at the top level, the root level, which is just the node A. Then we go to the first level and we traverse it entirely, B, C, and D. Then we go to the third level and we traverse it entirely, so E, F, G, and H. And then finally we go to the fourth level and we traverse it entirely, I, J, and K. This is opposed to depth-first search, where we would traverse kind of branch by branch. We'd go as far deep in a branch as we could before moving on to another branch. So here we're kind of going wide. We're going through all the child nodes first, then through all the child nodes at a given level, etc., etc. So this sounds pretty simple, pretty intuitive. Why did I say it was difficult? Well, when you're tasked with actually implementing this in code, it becomes a bit harder. It becomes a bit more confusing. You start to ask yourself, okay, do I keep track of the first sort of child node, go through all the siblings, remember that first child node, then go through its child nodes, but then go back up, and it just gets confusing, right? Try it yourself, you'll realize that it gets confusing. But so the way we can make this pretty easy to solve is by using an additional data structure called a queue. So I'll write it here in the bottom. We're going to be using a queue. So if you're not familiar with queues, I would definitely encourage you to look up the category queue that we have here on algoexpert.io. We've got a few questions on those. A queue, in a word, or in a couple words, is a data structure that follows this rule of first in, first out. In other words, anything that we put in the queue, or rather the first thing that we put in the queue is going to be the first thing to come out of it. And we can pretty simply create a queue just using a sort of array, right? A Python list or a JavaScript array. And so what we're going to do, I guess I'm not even going to go ahead and explain it. I'm just going to go through the example and it's going to make a lot more sense. So we're going to start at the root node, which is the A node. And we're going to add the A node to our queue. So I'm going to add it here. Okay. And on top of this queue data structure, we're also going to declare a variable, which is going to be called current. It's going to kind of represent our current node. And here we're probably going to be using a while loop. And we're going to say while the queue is not empty, so while we have nodes in the queue, we're going to pop a node from the queue in a first in, first out fashion, meaning the first node that we put in is going to be the first one to come out. And we're going to make that node the current node. So in here, in this case, we only have one node in the queue, node A. So we're going to grab it, pop it from the queue, and make it our current node. Once it's our current node, we're going to first add its name to the final array. So I'm going to draw the final array here in brown so we can add A to the final array because A is our current node. And then we're going to add all of the child nodes of A, which are B, C, and D, to the queue in that order. So we're going to add B, then C, and then D. And so now we can get rid of A. We erase A. And we see that our queue is not empty. There's stuff in our queue. So we pop B from the queue in a first in, first out way. Remember, B was the first node we put in. Whoops. So we grab B and we move it to our current node. We make it our current node. Once B is our current node, we grab its name and add it to our final array. And then we grab its two children nodes, E and F, and we add them to the queue, E and F. So now we can erase B, and we can pop the next value from the queue, which is C. Why are we using C? Again, this first in, first out idea. C was the first node amongst these 4 nodes that we have here to go into the queue. So we pop it, we pop it first, and we make it our current node. Once C is our current node, we can add its name to the final array, and we can grab its children nodes and put them in the queue. But you'll notice we don't have any children nodes here. C is just, it doesn't have any children nodes. So we can just erase it. We're done with it. Pop the next value, which is D. Make D the current node. Grab its name, first and foremost. Add it to the final array. And then grab its two children nodes, G and H, and add them to the queue. So we're going to add G and H. So now we're done with D. We can pop the next node from the queue, which is E. Add it to the current node. I'll start moving these nodes to the left so we have a bit more space. Put E in the final array. Grab any child nodes that E might have and put them to the queue. But E doesn't have any child nodes, so we can just wrap up with E and erase it. Then we're going to grab F, our next node, make it our current node, add its children nodes, so I and J, and also obviously don't forget to add F to the final array. Now we can erase F, move on to J. So we're going to grab J from the queue, make it our current node, add the child node that J has, which is K, add K to the queue, add J to the final array. And so you can kind of see how we're doing this, right? We add a node to the queue, or rather we pop a node from the queue, we add its name to the final array, and then we add all of its children nodes to the back of the queue. And then we pop the node from the front of the queue. And that's how it goes. So now we erase G, and you'll notice that for the rest of these nodes, none of them are going to have children nodes, right? H is at the end of its branch, I is at the end of its branch, J and K are also at the end of their branches. So here we're just going to, pop them one at a time. So pop H, put it as our current node, add its name, add H's name, and then, pop I, and so on and so forth. So I'm not going to go through the end of this example. We can just add I, J, and K here. And so now we get to a point where our queue is empty. And when our queue is empty, we can kind of break out of our while loop. As we mentioned earlier, we're probably going to be using a while loop. And we are done with breadth first search. So we can erase this. If you're not convinced, we can grab this array that we just built and compare it to our initial solutions array. And you'll notice that it's identical, right? We've got A, B, C, D, E, F, G, H, I, J, K. And we're done. So now before we jump into the code implementation, let's cover the space-time complexity analysis of breadth-first search. So the space-time complexity analysis is a bit involved, mainly because we're going to be dealing with two different variables. So in a graph, you've got what's called vertices and edges. Vertices are kind of the nodes, right? The different points in the graph. So here we've got A, B, E, F. These are all vertices. Edges are the things that connect these nodes. So for instance, this line here is an edge between A and B. Or this line here is an edge between B and E. And so the time complexity of this algorithm, I'll write it here, is actually going to be O of V plus O of E. Or rather, O of V plus E. So let me erase that and say it's going to be O of V plus E, where, again, V is the number of vertices in the graph, so the number of nodes, and E is the number of edges connecting these nodes, okay? And the reason it's O of V plus E, this might not seem intuitive at first, but it makes a lot of sense once you really dive into it. Think about what we're doing throughout the algorithm, right? We traverse all the nodes at one point, right? There comes a point where we have every node as the current node, and we grab its name and add it to the final array, right? And so in those cases, like in that case, we traverse every node for sure, and so we have O of V. For every vertex V, we traverse it and add its name to the final array, so we definitely have O of V in our time complexity. But on top of that, for every node, we add its children nodes to the queue. And so how many children nodes does a node have? Well, it has as many children nodes as it has edges coming out of it. So for instance, A has 3 children nodes because that's 3 edges coming out of A. B has 2 children nodes, E and F, because it has 2 edges coming out of it. Whereas I does not have any children nodes. It's at the bottom of its branch. So there are no edges coming out of I. And so when we're dealing with I as our current node, we do an operation where we add its name to the final array, but then we don't loop through any of its child nodes. So in other words, we only loop through as many edges as we have, and then we append to our final array the names of as many vertices as we have. And that's where we get this O of V plus E time complexity. Now, in terms of space complexity, the space complexity is going to be O of V. So space is going to be O of V. So there are 2 reasons it's O of V. One is that we're storing an array of V node names, right? That's just the question asks us to store that array. So from that point of view, it's O of V. But from the point of view of just the breadth-first search algorithm, we have this queue data structure, right, that we built at the bottom here. And this queue data structure holds nodes during the algorithm. Now, in most cases, it doesn't hold that many nodes at once. But you can imagine this would be kind of the worst case, where we could have a graph that would have a root node, right, A, and then all the child nodes would be direct children of A. So like B, C, D, E, F, etc. They would all be direct children of A. And so in that case, we would have a queue that would hold all of these nodes at once. And so there would be a point in time where our queue would be holding n minus 1 nodes, or rather v minus 1 nodes in it, because v is vertices, v represents the number of nodes. And so in the worst case, breadth first search is going to run in O of v space complexity. Again, for our particular question, it's O of v regardless because we're keeping track of this final array of v node names. But so that's it for the space-time complexity analysis of breadth first search. Make sure to wrap your head around that. And now let's dive into the code implementation. All right, so we've got our node class defined. It's a pretty simple class. Every node has a name and then has a children array, which is initialized to an empty array. Then you can add children by just appending a new node to this children array. And so then we've got our breadth first search function defined, which takes in an array, which is going to be the final array that we're going to return with all the names of the nodes inside. So the first thing we're going to want to do is to initialize our queue. And as I mentioned in the conceptual overview of the algorithm, our queue can just be, JavaScript array, a Python list. And we want to initialize it to hold the first node, right? The root node, the node on which we're calling breadth first search. And so we're going to pass in a self, which is, the node that we're calling breadth first search on. We're going to pass that in to the queue array. We're going to initialize the queue array to have self. And so once we have that, we can get into our while loop. And we can say while the length of the queue is greater than 0, in other words, while the queue is not empty, while there are nodes in the queue, let the current node, remember the current variable that we had declared, let the current node be queue.pop at 0. We take the value at index 0 in the queue, pop it out, that's the first in, first out mechanism, and set that to the current node. Then the first thing we do is we append to our array the name of our node, so current.name. And then finally, for child in current.children, for every child node that we have in our current node, append those children to the queue. So queue.append child. And once that's done, we can get out of the while loop and just return the array. So you can see it's pretty straightforward. It's not that long of an algorithm, but it is a bit involved because it uses this queue. So we initialize the queue to have our root node at the beginning. And then while the length of the queue is greater than 0, while the queue is not empty, set the current variable to be the first in, first out node, right? The node at the beginning of the queue. Append the name of the current node to our array. And then for every child node you have in your children of the current node, append that child to the queue, to the back of the queue. And then at the end, once your queue is empty, you're going to break out of this while loop and you're going to return the array. So this is going to run in O of v plus e time. You can put this in lowercase v plus e time, where v is the number of vertices in our graph, and e is the number of edges in our graph, and the space complexity is going to be O of v space. Again, O of v space mainly because we're returning an array of length v, but also because in the worst case, our queue might have at one point a length of v minus 1 if our root node has every other node in the graph amongst its direct children. So that is it for this algorithm for breadth first search. I hope this video is helpful and informative. Be sure to understand how it works, and I'll see you in the next video.